The title is here. Can we move up a little, Tatiana? No, just move up. Okay, so the talk will be based on these three papers, but basically maybe in major part on this paper with Adolf Mirotin from Belarus. But the idea appeared in the first paper written in 2018 and published in 2019 when I was on Fulbright, State University of New York, together with Kehedzu and Professor Stefan Samko. We started to study operators of the following type. No. Wait. Integral over disk, certain kernel W, F phi z W, GH W. This would be our model operator, where phi z or W is Möbius transform, and GH is a Haar measure invariant with respect to Möbius transform. Later I will give definitions of everything. This operator appeared as a continuation of two theories which are similar to each other but different. One theory is a theory of operator with homogeneous kernels. And another theory is theory of Hausdorff operators. For the reference, I would say there is a book by Karapetyants and Samko, but not me, Nikolai Karapetyants, Stefan Samko. And maybe main reference for Hausdorff operators, Ilya Livland and Moritz. Ilya Livland and Moritz. I don't remember the name. But you see,
the strong condition of the F, or it's
no, wait. I will give definitions later. Now I'm just giving some introduction. Okay. The idea how we came to this operator. The idea was to have to translate what we know for operators with homogeneous kernels, because mainly these operators appeared in real analysis, and the whole theory was developed in the framework of real analysis. And we thought to transfer the theory to the complex state, and actually to the complex frame, and actually with another researcher, Gerard Avetisian, we thought a little about how to do this. We took these operators with homogeneous kernels and recalculated them, passed them to the unit disk, and we obtained some strange constructions, and we didn't find any example inside of this class of operators. So we just left this study, and we understood that we cannot just copy. We can use ideas, but maybe we have to invent different constructions. That's how we came to this construction, because this construction possesses some invariance property. I will show this property later, which is kind of feature for these operators and also a feature for operators of Hausdorff type. Okay, so can we move? So that's operator 1.1. I already have it here. That operator appeared in our paper with Zhu and Samko. Here we have definition of the Möbius automorphism, and maybe later we'll have here. Stop here. Here you have the definition of Haar measure, and that's invariance properties that I just mentioned. You see, you can put Möbius transform here, or you can put Möbius transform here. Why this operator is of interest? We can move first. Because this is nothing but, okay, a straight generalization of very known Berezin transform. Berezin transform plays a very nice role in complex analysis, similar to Poisson transform, but with the exception that instead of integration over boundary, we integrate over union disk. It applied to problems of compactness or boundedness of operators, many important features connected to this transform. So at least this important operator inside of our class. It's very important to have some good examples. So at least Berezin transform is inside. So it's worth to study operators. In particular, you'll have Berezin transform when k of w in this particular case equals to 1 minus w squared. In this particular case, we obtain Berezin transform. Still, there are more operators in this class, like maximal operators studied by Miroslav Pavlovich and Mian Rakhmatelevich, and also green potential for invariant Laplacian. But I will not show all further examples. For me, it's sufficient just to mention that this important operator is inside of our class. What actually we did, we just take, instead of this concrete kernel, just take a general function. And we're getting more general operator. That's what we study. Okay? Okay. Also, if we take a look at the weighted Berezin transform with this weight, then, then you can think about this function as a kernel, right? Or otherwise you can think as a weight and still you can put here another kernel. So this is another way to generalize it. Not just this particular measure, but take another more general measure. That's what we did with Mirotin, with Professor Mirotin. And of course, Berezin transform, the weighted Berezin transform, also is a very nice construction because when lambda parameter moves, it possesses some approximation property. It's not just generalization just for curiosity. This lambda parameter works very well in the theory of approximations. Okay, so let's go further. No, I already stated. So what exactly we study? We generalize kernel, we put here kernel, and we put here a general measure. Okay, that's what we study with Mirotin. That's what I will be speaking about today. And also, next generalization in what space? Also in weighted space. So here we study also some weights V. Okay, so what kind of weights? We have to provide a definition for this. Weights which are admissible for us. Okay, let's go further. Maybe stop here. You see, this operator that we called operator Berezin-Hausdorff-Zu, because first I learned about this operator from Kehit-Zu. He studied this type of when k is 1. This operator appeared in some calculus, but he said to me that this operator is very small. Indeed, it's very small, because if you just cancel k, then the image of action over arbitrary allomorphic function is just monomial constant plus alpha plus beta z. So he takes function, cuts it. After a function, he preserves only zero coefficient and first coefficient. So alpha plus beta z. He cuts functions. Yeah, that's why this operator, even what was different between this operator and this operator, you just switch variables. And it looks like the same, but not. It's quite a different construction, quite a different operator. It's also of a great interest, and we have other papers with Mirotin and Grutsky dedicated to this operator, but I will not speak about this operator right now. Just mention that being similar to our operator is very different. Okay, so let's go further. Weights. I promised you to give definition of weights. So we will call Möbius weight, a function v is called a Möbius weight if this inequality holds true for a certain measurable function c. we call a function v a strong Möbius weight if you will have also lower bound. Okay, C prime also a measurable function. Okay, examples of these weights. So this nice weight is a Möbius weight. Moreover, divided by this weight is also a Möbius weight. Also, further. Moreover, any power of this 1 minus z squared is a Möbius weight. I want to stress attention that these weights are very important because we are on the unit disk, and when we speak about holomorphic functions, so the only important is what's going on when approaching to the boundary of the unit disk. So these weights are very important for in the context of these considerations. And this power weight is the strong Möbius weight for the case when alpha is non-negative. Okay? So now I repeat that we study operator 6.1. K is a kernel, a measurable function. Mu stands for a positive radon measure on the unit disk. And we study these operators in framework of these weighted LP spaces with weights as I specified above. Okay, further up to this stop. Okay. So first theorem condition involves the upper boundary for the weight. If this construction belongs to L1 with respect to this radon measure d mu, then the operator is bounded in weighted LP, and the constant doesn't exceed this constant n index C. Okay. Stop. When you consider particular cases of measure, then you can formulate more easy conditions, more simple conditions like this, with this upper bound like calculated immediately from the formula. Okay, further please. Stop. Also, in framework of study of operators of this type, we have sufficient conditions, but it's great also to have necessary conditions. Necessary conditions usually we obtain when kernel is non-negative. It's natural. So if kernel is non-negative, then, well, I will not read the theorem. For instance, here you have almost similar to the sufficient condition. So instead of upper bound, here we have lower bound. Yes? And here you have minus sigma over p. You remember we had minus 1 over p, and sigma, I guess this is misprint. Sigma must be greater than 1. So it's almost the same up to epsilon. It's 1 minus epsilon. So written here, sigma is the same like, right? It's the same like written 1 minus small epsilon, right? So we almost close to the sufficient condition, right? So the difference is epsilon. But it's life is like this. I mean, you know that not always necessary conditions repeat the sufficient conditions. Sometimes different, but sometimes they do repeat. In particular cases, when we restrict to the unweighted case, then we have if and only if condition, like this. And also, it is important to show example to show when kernel is of this particular type, then we can give necessary and sufficient conditions in terms of the power of the kernel alpha. So please remember this condition, because I will refer to this condition later again. Okay.
Would you please just go up a little bit? Let me see that alpha in the first one. The alpha in go up a little bit. C1
Yes, in insufficient, wait, I repeat that insufficient, you have minus 1 over p. So you have here minus 1 minus epsilon over p. In other words. Okay? Okay. So also, it is of interest to take another look at sufficient conditions, and again to try to use what we know from theory of operators of homogeneous kernels, and this theory gives us kind of different conditions. For instance, here in terms of these integrals, and here the function kz is involved. Function kz is a normalized galomorphic kernel. I will not write it down. I hope next on the next slide it will appear. Wait, stop. Come back. I just want to show this. So under this condition 7.4, if this construction less than infinity, then operator k, our operator k, is bounded between LR and LP, and the operator norm does exceed this constant. Okay, further please. Again, different conditions. Again, written in terms, maybe I'll write down this kz. As I said, kz are normalized kernels. Kzw equals to 1 minus z squared, 1 minus z w, I guess like this, squared. So just normalized galomorphic kernels. Okay. We have k1 depending on p sigma, k2 depending on q sigma, these integrals. If k is radial, then you can rewrite this formula in this form. But the theorem is as follows: if there exists a sigma such that this constant in less than infinity, then the operator is bounded in LP, and the operator norm does exceed this infimum. Okay. Again, to formulate necessary conditions instead of supremum, you remember we had supremum, but then now we need to put here infimum, and of course we have to consider the case of non-negative kernel k. Okay, let's move further. Okay, stop. Under these conditions, kernel k is non-negative, and if operator k is bounded, then these constants are fine. This is kind of substitute of necessary conditions. Please go further. For this particular case, a little bit up. Okay, a little bit more. Okay. For this particular case, we can formulate conditions in terms of alpha. You may say that kind of strange conditions, but not, because if you remember in previous theorem, sigma is greater than -1. So imagine what's going on if we formally put sigma to be -1. Then we will have, then the maximum will be attained here. For instance, we have -1 plus 1 over p. The same condition that we had obtained by different method. With the only difference that we have to write here more greater than, not in the first corollary we had better result, strictly greater. But from here, when you try 10 to go to -1, you can write only this. But at least I can state that these two different approaches coincide on this particular example up to some problems that appeared that there is no coincidence in terms of here's strictly, and in second case is greater. Okay, further please. Approximations. How much time I have? Oh, good. Approximations. You see, when we wrote a paper with Professor Liefland about Hausdorff operators a couple of years ago, our idea was to impose some characteristical conditions on Hausdorff operators that this condition would be characteristical for arbitrary Hausdorff operators. So we thought about 5 conditions. that we would say that if an operator of certain form possesses such properties, then we will call this operator Hausdorff operator. Well, the discussion about what to call Hausdorff operators, it's a long discussion, and Ilya Liflin can say about it much more than I. So I will not continue. I just want to stress attention that among these 5 features, we mentioned approximation. We mentioned that approximation must be one of the characteristic features of Hausdorff class of operators. So it means that inside of this class, there should be approximative constructions. So the same applies to this, which is not Hausdorff, it's Hausdorff-Berezin, but it's still close to the Hausdorff class. You see, we can just move up, down, okay, more. You see, you can move next slide. If you formally put here epsilon equals to 0, then what we have? Phi z of 0 equals to z, and formally I'm saying, you can move f of z outside, and you have approximation, right? So if you impose these conditions on the kernel, then you have classical approximations, right? And formal statement is in this following theorem 8.15. I will not read these conditions, but under the conditions written in the theorem 8.15, the operators given above are identity approximations in LP, in weighted LP. Namely, this property holds true. Okay? Okay. Another idea. You see, the first idea was to put epsilon inside of the Möbius transform. But this is another idea that related, you remember I mentioned about the property of Berezin transform. It provides some kind of approximation. So since this operator or these operators inherit in some sense properties of Berezin transform, there should be property also of approximation with respect to some parameter. So given a parameter lambda, let k lambda be parameterized family of non-negative kernels such that this condition 9.4, these conditions 9.4 and 9.5 are satisfied. Then we consider this construction, and we will prove that this construction provides us with approximation. As an example, you can say that these conditions are kind of strange, but not. For instance, for this particular case, you can take these kernels. If you take Radon measure to be just plain Lebesgue measure, that you come to nothing but the Berezin transform, which is known to provide approximation in some certain sense when lambda parameter goes to infinity. So these conditions are not strange, that these conditions are quite natural. Okay, so let's go further. Identity approximation. You remember this constant from the theorem of boundedness of operator, this extra condition we have. And assumptions 9.4, 9.5 that I mentioned on the kernel, right? So I will not read this theorem, but under the conditions written, under the conditions written in this theorem, these constructions provide approximation in the sense that the formula 9.7 holds true. Okay? And I repeat that this is a different idea of how to construct approximation from this class of operator. And one short note that for this, again, we come back also to examples, particular cases. For this particular case, this condition, you remember I said this extra condition, is automatically satisfied. So for some concrete examples, we don't need to check this condition. Okay. Well, you see, maybe I skip applications because I don't have time, I guess. Maybe that's it. That's all I wanted to tell you, to say it for today. Thank you.